If you're currently an aviation maintenance technician student, you know there's just a massive amount of information you need to get through. But sometimes the most critical stuff, well, it's the oldest. Welding as a craft goes way back. I mean, Bronze Age kind of back. Yet modern welding, specifically being able to join steel tubing just right, that's the reason the first commercially successful aircraft even flew, those early steel tube frames.
It really is the original way we build airframes. And today we're aiming to cut through all the dense technical guides. We're specifically focusing on you as you're working through Chapter 5 of your AMT Airframe course, the Welding chapter.
Right. Our mission for this deep dive is pretty focused. We want to pull out the fundamental principles, those really critical safety limits you just have to know, and the exact specialized repair techniques you'll need to memorize. We've dug into some deep operational sources here, covering everything from the physics, like why aluminum just collapses under heat, to the really precise dimensions you need for structural steel tube repairs.
Yeah, we're trying to get beyond just, we're reading the definitions in the chapter. We want you to understand the why behind every single critical rule. So let's start right at the beginning. Let's define what welding actually is in this context. Okay, at its absolute core, welding is basically a process that joins metal together. You do that either by melting the pieces until they fuse, or sometimes, historically, by hammering them until they unite. It takes dexterity, definitely focus, and honestly lots and lots of practice. Our sources really emphasize this point. It's not some secret art held by only a few. It's a skill that pretty much anyone with a decent mechanical sense can learn with good training.
But the world of welding is huge. For aviation maintenance, what are the main categories we need to focus on? The big three.
We generally group them into gas welding, electric arc welding, and electric resistance welding. Now, historically, gas welding, that was the king for a long time. But today, electric arc, and that includes processes like TIG and MIG, that's absolutely essential for modern aircraft construction and, crucially for you, repair.
And that big shift, that happened mainly because the materials themselves changed over time, didn't it? Those early planes, the classic biplanes, the early monoplanes, they used that strong, thick-walled steel tubing.
Exactly right. Those early airframes were built with SAE 4130 steel tubing. It's pretty forgiving stuff, handles the heat from gas welding quite well. But, the industry always wants more speed, more range. We needed to lose weight badly. So there's this huge shift towards lighter metals, aluminum, magnesium, and then eventually titanium.
And that must have created some massive technical headaches. I mean, steel glows red, it softens up gradually, gives the welder some warning, some time to react. Aluminum just doesn't do that, does it?
Precisely. That's a key difference. Those lighter alloys, they often behave completely differently under heat. Aluminum, for instance, conducts heat away from the weld zone like crazy, way too quickly sometimes. And titanium, it reacts, and reacts violently, with the oxygen and nitrogen in the air if it's molten. So this fundamental change in materials had basically forced the rapid development of electric arc processes. Processes that could deliver really focused heat and, crucially, protect that heat zone from the atmosphere.
Okay, let's circle back to the classic first method then. Gas welding, specifically oxyacetylene. What kind of intense energy are we really talking about here?
Well, we're generating heat by burning a fuel gas, usually acetylene, but boosting it with pure oxygen. The result is this incredibly high temperature flame, and you use that to bring the edges of the metal parts right up to their molten state so they fuse. That oxyacetylene flame, when it's perfectly balanced, hits about 6,500 degrees Fahrenheit. That's a phenomenal amount of localized heat.
Wow, 6,300 degrees. How tough is it to learn to control that kind of intense heat, especially on thin aircraft materials?
It takes real finesse, no question. You're wielding a heat source that can melt steel in just seconds. Historically, gas welding was the standard for production work, especially on materials thinner than about 316 of an inch, right up until the mid-1950s or so. It lost out to electric welding mostly for economic reasons, speed, automation potential. But here's the key thing for you, the AMT student. Oxyacetylene is still incredibly popular. It's proven, it's cost-effective, and it's widely used for repair operations today, especially in the thin-walled steel tubing you find in older airframes where actually that slightly less intense, more controllable heat output can be a real advantage.
And acetylene is the main fuel, but you mentioned there's an alternative, mostly used for aluminum.
Right, that's hydrogen. You can substitute hydrogen gas for acetylene, particularly if you're working on non-ferrous metals like aluminum. But there's a trade-off, a significant one. You lose a lot of that top-end heat output. Hydrogen only gets you to about 4,800 degrees Fahrenheit. Now, that lower temperature can actually make heat control a bit easier on thin aluminum, which is good. But it means you need more patience and arguably better technique to really get a proper deep fusion weld.
Okay, since knowing oxyacetylene is still absolutely required for airframe repair, let's walk through the typical setup. If you're looking at Figure 5.1 in your textbook, what's the essential equipment checklist? What must you have?
Right, the list is non-negotiable. You absolutely need the two cylinders, one for acetylene, one for oxygen. You need the specialized regulators for each, with their gauges showing cylinder pressure and working pressure. You need the correct color-coded hoses, red for acetylene, green for oxygen. The torch assembly itself, of course, with a selection of different size tips for different jobs. Safety goggles are mandatory, and they need the correct shade lenses for the work you're doing. A flint lighter, not matches, or a cigarette lighter, the specialized wrench, usually a T-wrench, for the acetylene cylinder valve. And maybe most importantly, an appropriately rated fire extinguisher right there with an arm's reach ready for immediate use. No excuses.
Let's really focus on the gases for a minute, starting with the one that presents the biggest safety challenge, acetylene. We know it's the fuel, but why is it so chemically unstable, and how do they actually store it safely in those cylinders?
Acetylene is just a highly energetic gas by its nature. If you compress it in its free state, just on its own, to only 29.4 psi, which isn't very high pressure, any slight mechanical shock like dropping the tank, even bumping it hard, can trigger a violent explosion. It decomposes extremely rapidly. So to get around this fundamental physics problem, acetylene cylinders aren't empty inside. They're packed solid with a porous filler material, things like kapok, charcoal, diatomaceous earth, historically asbestos even. And this porous mass is then saturated with liquid acetone. The acetylene gas is then dissolved into the acetone under pressure. This stabilizes it, holds it safely, allowing storage at much higher pressures than you could ever manage with free acetylene gas.
And that chemistry leads directly, like you said, non-negotiably to the single most important safety rule in gas welding.
Absolutely. It's the cardinal rule. Because of that inherent instability risk, the working pressure gauge on the acetylene regulator, the one controlling flow to the torch, must never be set to exceed 15 psi. Not for welding, not for cutting, never. If you go above 15 psi, you risk pulling acetylene gas out of the acetone solution faster than it can be replenished. You increase the concentration of unstable free acetylene gas in the regulator and hoses and dramatically increase the risk of detonation. 15 psi is the absolute limit. Memorize it.
Okay. Oxygen, on the other hand, that's the safe gas in this pairing, right? Colorless, odorless, doesn't burn itself. It just acts as the accelerator.
Exactly. It's purely the oxidizer. Its only job is to increase the rate of combustion of the acetylene, pushing that flame temperature way up to the 6,300 degrees we need for efficient welding.
And we should probably just briefly mention the inert gases here, too. Argon and helium. They're crucial for TIG welding later, but they aren't fuel. They play a different role.
Right. They're purely protective shields. Argon and helium are used as shielding gases in TIG, MIG, and plasma welding. They flow out of the torch nozzle and form a protective blanket over the molten metal puddle. This blanket displaces the surrounding air, preventing oxygen and nitrogen from getting into the molten weld and contaminating it, which would cause brittleness and weakness.
Okay, moving on to the hardware side. The regulators, their job is to step down that high cylinder pressure to a usable working pressure. But we see two types mentioned, single stage and two-stage. Is there a real advantage to the two-stage regulator?
There is, especially for precision work. The two-stage regulator is mechanically more complex, but superior in performance. It reduces the high cylinder pressure down to the working pressure in two distinct steps, using two sets of diaphragms and springs. The result is a much more constant, stable outlet pressure and flow rate delivered to the torch, even as the pressure inside the storage cylinder drops significantly as you use the gas. That stability is really crucial when you're doing delicate, consistent welding, especially on thin aircraft skins or tubing where tiny fluctuations in heat can cause big problems.
Now, cylinder handling seems simple, but you mentioned improper handling, particularly with acetylene, can lead to serious system contamination and even dangerous flashbacks. What's the key rule here?
Cylinders must always be stored and transported upright, vertically. If you lay an acetylene tank on its side, that liquid acetone stabilizer, the stuff holding the acetylene safely, can actually spill out of the porous packing material and potentially get into the valve. If that liquid acetone then gets drawn into the regulator, the hose, or worse, the torch itself, it contaminates the system. It can cause erratic flame behavior, fuel starvation, and potentially trigger a dangerous flashback where the flame burns back into the equipment instead of out the tip.
And the procedure for opening the cylinder valves is also very specific, different for oxygen and acetylene, again for safety reasons.
Yes, very specific. The oxygen cylinder valve has what's called a double seat valve. You should open it fully, all the way until the back seats. This seals the valve stem packing and prevents leaks around the stem while it's under pressure. However, the acetylene valve is different. It must only be opened about 1/2 turn, maybe 3/4 at the absolute maximum, never wide open. This is a critical safety procedure done purely for quick shutoff. If you have a fire breakout at the torch, or if a hose ruptures, you need to be able to slam that fuel supply off instantly without fumbling. 1/2 turn makes that possible. Also, a related point. Never completely drain cylinders. Leave at least 20 psi, maybe more like 50 psi, in them. This residual pressure prevents any possibility of reverse flow or atmospheric contamination getting back into the cylinder.
Let's talk about the hoses. There's a visual safety cue with the colors and a physical one with the threads.
Right. The color coding is standard. Red for acetylene, the fuel gas. Green for oxygen, the oxidizer, easy to remember. Red means danger fuel. And the fittings are different too. Acetylene hoses and fittings use left-hand threads, which tighten counterclockwise. They often have a groove cut into the nut as a tactile indicator. Oxygen uses standard right-hand threads. This physical difference makes it impossible to accidentally connect an oxygen regulator to an acetylene cylinder, or vice versa, a crucial built-in safety feature.
And built-in safety devices like check valves and flashback arrestors. The text says flashback arrestors are highly recommended. What exactly do they do, and how are they different from a simple check valve?
They are absolutely vital safety components. Highly recommended is an understatement in my book. A simple check valve only stops reverse gas flow. It prevents, say, oxygen from flowing back up the acetylene hose if pressures get unbalanced, which could create a dangerous mix. But a flashback arrestor does much more. It's designed to stop an actual flame front, a situation where the flame is burning inside the hose or torch, traveling backwards at high speed towards the regulators and cylinders. It typically contains a flame trap element, often sintered metal, that quenches the flame, and usually a heat-sensitive cutoff valve as well. If you ever hear that distinct shrill hissing or squealing sound that indicates a flashback is occurring, you need to immediately shut off the cylinder valve's oxygen first, then acetylene correct the cause, like a clogged tip or wrong pressures, and make absolutely sure your arrestors are functioning correctly before you even think about relighting. They are potentially life-saving devices.
Okay, for the actual work, the torch itself is often specialized for aircraft maintenance, right? Especially working in tight spaces.
Yes, we tend to use what's called the equal pressure torch design. It operates with acetylene pressure anywhere between 1 and 15 psi. Mixing the gas is usually right in the torch head or tip. It's generally robust and considered less prone to flashback than older injector-type torches. And specifically for aviation maintenance, technicians often really favor small, lightweight models. Brands like the Smith Airline or the Miko Midget are popular. They're designed to minimize fatigue and improve maneuverability when you're maybe contorted under a fuselage or working inside an engine mount structure trying to make tiny, precise welds in awkward positions.
And choosing the right torch tip. The book stresses that the tip size controls the amount of heat, not the actual flame temperature itself. That seems like a really important distinction.
It's absolutely fundamental to understand that. The flame temperature itself, around 6,300 degrees off for oxidizing, 5,850 degrees off for your neutral, is set by the gas chemistry. The size of the orifice in the torch tip dictates the volume of the gas mixture that can flow through it per unit of time. So a larger tip delivers a larger volume of burning gas, which means more BTUs, more sheer quantity of heat is delivered to the workpiece. You absolutely must consult the manufacturer's charts, which recommend specific tip sizes based on the type of metal and its thickness. If your tip is too small for the job, you won't deliver enough heat quantity to get proper fusion and penetration, leading to a weak superficial weld. If your tip is way too large, you'll deliver too much heat too quickly, risking blowing holes right through thin metal or severely overheating the base material. Oh, and a related issue. A backfire, that little pop or momentary flame extinction at the tip, often followed by reignition that's frequently just a sign that the tip orifice is partially clogged with soot and metal spatter. Cleaning the tip usually fixes it.
Lastly, for equipment, the lighting procedure. Always use a friction lighter, the flint striker type. Why is using a match or a regular lighter so dangerous?
Always use a flint striker or a stationary pilot flame setup if you have one. Never use matches or a disposable lighter. The reason is gas accumulation. When you first open the torch valves to purge the lines or start the flow, you get a small cloud of unburnt fuel gas momentarily accumulating around the tip in your hand. If you put an open flame like a match into that cloud, it can ignite instantly, potentially engulfing your hand in a brief but intense flash fire. Very nasty burns can result. The sparks from a flint striker are hot enough to ignite the flowing gas mixture right at the tip, but they don't present the same large ignition source risk as an open flame. It's a simple rule, but critical for safety. Okay, now we get right into the heart of the technique, generating the right flame and controlling it. By carefully adjusting the ratio of oxygen to acetylene using the torch valves, we can create three distinctly different types of flames. And selecting the correct flame type for the specific metal you're working on is absolutely crucial. It literally determines whether you'll succeed in making a sound weld or just damage the material.
All right, let's break down those three types, starting with the one that's probably used most often, the general purpose flame.
That would be the neutral flame. As the name implies, it's produced by a chemically balanced mixture of oxygen and acetylene. Roughly 1-to-1 ratio by volume actually consumed, though the regulator settings might look different. At the very tip of its sharply defined, brilliant white inner cone, it reaches about 5,850 degrees Fahrenheit. This is the standard flame for welding most metals, especially common carbon steels like 4130. Why? Because it's chemically neutral. It doesn't add excess carbon to the weld pool, which would make it brittle, nor does it add excess oxygen, which would burn the metal and weaken it. When you apply a neutral flame correctly to steel, the molten puddle should look quiet, clear, maybe with a few sparks, but generally calm. That allows for a smooth, strong fusion weld without changing the base metal's properties significantly.
Okay, so neutral is the baseline. What happens if we deliberately add too much acetylene? We get the carburizing, or sometimes called reducing, flame.
Exactly. This flame results from an imbalance where there's excess fuel gas, excess acetylene. The flame temperature actually drops slightly, down to around 5,700 degrees Fahrenheit. The key visual identifier is a greenish, feathery secondary cone or veil that extends beyond the sharp white inner cone. The length of that greenish feather tells you just how much excess acetylene you have. This flame is specifically used for certain applications like welding high-carbon steels, where adding a little carbon isn't detrimental, for hard-facing operations, and importantly for some non-ferrous alloys like aluminum or nickel. The excess carbon can sometimes help reduce surface oxides on those metals.
And the third type, the hottest one, but also potentially the most damaging if used incorrectly.
That's the oxidizing flame. We create this one by deliberately running an excess of oxygen, maybe closer to 2 parts oxygen, for every 1 part of acetylene being consumed. This is the hottest flame of the three, reaching up to that 6,300 degrees Fahrenheit mark. Visually, the inner cone becomes much shorter, maybe a bit more pointed, and often takes on a slightly purplish tinge. The outer flame envelope is also shorter and much noisier. It kind of hisses more. Now, using this oxidizing flame on regular steel is absolutely disastrous. It causes the molten metal to foam up, spark excessively like a sparkler, and literally burn the base metal, oxidizing the iron and carbon. The resulting weld is weak, brittle, and full of porosity. Just don't do it on steel for fusion welding.
So if it's so bad for welding steel, what's its main use in aircraft maintenance then? Why learn about it?
Its primary application is actually in brazing, specifically when brazing steel or cast iron using bronze filler rods. It's also used sometimes for fusion welding brass and bronze alloys themselves. Remember, in brazing, you're not melting the base metal. You only need to heat the base metal hot enough to melt the filler rod. Because the oxidizing flame is so intensely hot and concentrated, it allows you to bring the heavier base metal up to the necessary brazing temperature, which is still quite high for bronze, over 800 degrees Kelvin, much more quickly and efficiently than a neutral flame could. It speeds up the brazing process considerably.
Okay, beyond the chemistry of the flame, there's also the mechanical aspect. Controlling a soft flame versus a harsh flame. You mentioned this is really vital for the thin-walled tubing and skins common in aircraft structures.
Absolutely crucial. You control the velocity of the gas exiting the tip, primarily by adjusting the working pressures at the regulators, and also by tip size selection to some extent. A soft flame has a lower exit velocity, even though it might have the same thermal output, BTUs, as a harsher flame from the same tip size at higher pressure. It burns more quietly, more gently. This soft flame is essential when you're welding thin materials or metals like aluminum that melt easily or conduct heat rapidly. A harsh, high-velocity flame acts almost like a miniature sandblaster. It tends to physically push the molten metal away from where you want it, making it really difficult to form a stable, cohesive puddle. It just blows holes in thin stuff. You achieve that desirable softness often by selecting a tip maybe one size larger than the chart minimum calls for, but then dialing back the working pressure slightly below the maximum recommended for that tip. This gives you enough heat volume, but delivered gently.
When we talk about the actual welding movement, the technique, the book mentions forehand welding is most common for aircraft repair. Why is that the default approach?
Forehand welding simply means the torch flame is pointed forward, in the direction that the weld seam is progressing. The filler rod is held ahead of the flame tip, and you dip it into the leading edge of the molten pool as noted. This technique generally offers the welder the best visibility of the joint ahead of the puddle and excellent control over adding the filler metal. It's ideal for the lighter gauge sheet metal and the relatively thin-walled tubing that makes up the vast majority of weldable aircraft structures.
And the alternative, backhand welding, that's more specialized.
Yes, backhand welding is the opposite. The torch flame points backwards towards the section of weld you've just completed. The filler rod is held between the flame front and the finished weld bead. This technique tends to concentrate the heat more effectively right at the weld puddle, and also provides a degree of preheating to the joint just ahead of puddle. Because of this, it's primarily used for welding very thick metals, heavy plate steel, things you rarely, if ever, encounter in typical airframe maintenance and repair scenarios. So forehand is what you'll mostly use.
Speaking of that molten pool, puddle control is key. What's the correct geometry? How close should that inner cone be?
You want to hold the tip of that brilliant white inner cone consistently about 1/18 of an inch away from the surface of the base metal. Too close, and you risk touching the cone to the puddle, causing contamination or backfire. Too far away, and you lose too much heat and don't get efficient melting. Once the puddle forms, you need to keep it centered right over the joint line. You maintain its size and fluidity using a steady, gentle motion, often a small semicircular or weaving motion, ensuring you're melting both edges of the joint evenly. This motion also helps distribute the heat and allows the filler rod, when you add it, to melt smoothly and fuse completely into the pool, rather than just dripping onto the surface.
And the filler rod itself, it's not just any metal wire. It has to be chemically compatible with the base metal to ensure the weld has the required structural properties, right?
Yeah.
Strength, ductility.
Absolutely critical. The filler rod material must be chosen carefully to match, or sometimes slightly overmatch, the desired properties of the finished joint, things like tensile strength, ductility, the ability to bend without breaking, and corrosion resistance must be compatible with the base metal being joined. You use specific rods for 4130 steel, different ones for aluminum, etc. Furthermore, the diameter of the filler rod is just as critical as the torch tip size. There's a relationship there. If your filler rod is too thin for the heat input you're using, it will melt too quickly, maybe even burn up before properly fusing, or won't draw enough heat away, potentially causing you to burn a hole in the base metal. Conversely, if the rod is too thick, it acts like a giant heat sink. It pulls too much heat away from the puddle too quickly, chilling it, preventing proper fusion and leading to insufficient penetration. It's a balancing act.
All right, let's shift gears now to the processes that dominate modern aircraft manufacturing and a lot of structural repair, electric arc welding. These methods use electrical energy to create that intense, focused heat we need. Let's start with perhaps the most traditional and widely known electric process, shielded metal arc welding, SMAW. Most people just call it stick welding.
Right, SMAAW, or stick welding, is probably the most common welding process used worldwide across all industries, not just aviation. It uses a consumable electrode, which is essentially a metal wire rod coated in a packed chemical flux. You strike an arc between the tip of this electrode and the workpiece, and the electrical resistance generates incredible heat, easily over 10,000 degrees Fahrenheit in the arc plasma. As the electrode melts, that flux coating does two crucial things simultaneously. First, some of it vaporizes in the intense heat, creating a localized cloud of inert or protective gas right around the arc and the molten puddle. This gas shield pushes the atmospheric oxygen and nitrogen away, preventing contamination. Second, the remaining flux components melt and form a liquid slag, which is lighter than the molten steel, so it floats on top of the weld puddle.
And that layer of molten slag provides protection as the weld starts to cool down.
Exactly. The slag stays liquid for a moment, covering the fresh weld bead. As the weld cools and solidifies, the slag hardens into a brittle, glassy crust. This crust continues to protect the still-hot metal from oxidation until it's cool enough to be safe. Then you chip the slag off. Historically, SMAW was used effectively in aircraft manufacturing. The example often cited is Stinson, who used stick welding for their 41 and 130 steel fuselage structures back in the day. However, and this is important, those welded structures absolutely required careful, mandatory heat treatment processes after welding to relieve stresses and refine the grain structure affected by the high heat input.
Okay, so stick welding has its place historically, but for you, the AMT student learning modern techniques, knowing which processes are generally not preferred for certain repairs, is just as important as knowing which ones are. Let's look at gas metal arc welding, GMAW, more commonly known as MIG welding metal inert gas.
Right. MIG welding is definitely an improvement over stick welding in terms of speed and efficiency, especially for production environments. Instead of coated sticks, it uses a continuous uncoated wire electrode that's fed automatically from a spool through the welding gun and into the arc. The shielding is provided by an external source of gas, usually an inert gas like argon or an argon-CO2 mixture, sometimes pure CO2 depending on the application, which flows through a nozzle surrounding the wire electrode. MiG typically uses a constant voltage DC power source, usually operating at relatively low voltage but high current.
So, if MiG is so efficient and widely used in other industries like automotive manufacturing, why is it generally frowned upon or even restricted for critical structural repairs on certified aircraft?
The limitation is quite severe for repair work, and it comes down to quality assurance. Because the filler wire is fed automatically, and the process often uses high currents leading to very rapid metal deposition and high heat input, it can be very difficult to visually verify the quality of the weld, especially things like ensuring complete fusion at the root of the joint. Determining if you got proper root penetration with MiG often requires destructive testing methods like cutting the weld open and etching it, which is obviously impossible for an in-service repair on an aircraft component. For certified aircraft repairs, you need a process where the quality, the penetration, the fusion can be much more readily assessed through careful visual inspection and common non-destructive testing, NDT methods, like dye penetrant or magnetic particle inspection. MiG makes that difficult.
Which brings us finally to the real gold standard for aircraft maintenance and repair welding. Gas tungsten arc welding, GTAW. Universally known in the hangar as TIG welding tungsten inert gas. This is the process that really fills most of your needs as an AMT.
TIG is absolutely the ultimate tool for most precision airframe repair work. Whether you're dealing with thin 4130 chromoly tubing, stainless steel components like exhaust systems, tricky magnesium alloys, or even thick aluminum sections, TIG handles them all beautifully. It's also known by some older proprietary trade names you might still hear, like HeliArc or HeliWeld, because helium was often used as the shielding gas early on.
And the fundamental difference with TIG, the thing that gives it such control, is that the electrode itself isn't consumed during the process, right?
Correct. That's the key. TIG uses a non-consumable electrode made of tungsten, or a tungsten alloy. Tungsten has an incredibly high melting point, so it can sustain the electric arc without melting into the weld pool. This arc burns at around 5,400 degrees Fahrenheit, providing the heat. But the filler metal, if needed, is added separately. You feed a filler rod manually into the edge of the molten pool with your other hand, very much like you do in oxyacetylene welding. This separation of the heat source, the tungsten arc, from the filler metal addition gives the welder incredibly fine, independent control over the heat input and the amount of filler being added. That's what allows for such precise, high-quality welds. And of course, that arc and the molten puddle is completely shielded from the atmosphere by a continuous flow of inert gas. Usually argon is preferred for manual TIG welding because it's denser than helium and provides a more stable, efficient shield, especially for out-of-position work. Helium might be used for thicker aluminum sometimes for its hotter arc characteristic.
Let's dig just a bit deeper into the power sources for TIG. The text makes a point about using DC straight polarity for steels and titanium, but needing AC for aluminum and magnesium. Why the difference? What's happening there?
Yes, this is a really important bit of material science related to surface oxides. When you use DC, or direct current straight polarity, that means the electrode is negative and the workpiece is positive, plus the electron flow is primarily from the electrode to the work. This configuration generates a deep, narrow penetration profile, which is excellent for getting good fusion on metals like mild steel, stainless steel, and titanium. Most of the heat is concentrated on the workpiece. However, metals like aluminum and magnesium have a major problem. They instantly form a very tough, refractory oxide layer on their surface when exposed to air. Think of aluminum oxide or magnesium oxide. These oxides have melting points far, far higher than the base metal itself.
So if you don't get rid of that oxide layer first, you can't actually fuse the metal underneath. The oxide acts like a barrier.
Exactly. You'll just melt the metal under the oxide skin, but you won't get a true fusion weld. The oxide inclusions will make the weld incredibly weak and brittle. AC, or alternating current, solves this problem because the polarity switches back and forth rapidly, typically 60 or 120 times per second. During the half cycle, when the electrode is positive, electrode positive or EP cycle, the current flow effectively blasts or ionically cleans the surface of the workpiece, breaking up and removing that tenacious oxide layer just ahead of the arc. Then during the other half cycle, when the electrode is negative, electrode negative or EN cycle, like DC straight polarity, the current does the actual heating and penetration work. So ACTIG provides this essential cleaning action needed to remove the oxides, allowing for sound structural welds on aluminum and magnesium. Without that AC cleaning, you simply cannot TIG weld these materials properly.
Okay, that makes perfect sense. Finally, in the electric arc category, let's briefly touch on plasma arc welding, PAW. This sounds like the most advanced, often automated technique.
PAW is definitely a more specialized higher-tech process. It's developed back in 1964, building on TIG principles, but aiming for even greater energy concentration and control, especially for automated applications involving miniature or high-precision components. Like TIG, it uses a non-consumable tungsten electrode to establish the arc. But in PAW, this electrode is positioned inside a specially designed nozzle, usually made of copper, which has a very small, fine-bore orifice at the end. A flow of inert gas, usually argon, is forced through the arc and then constricted as it passes through that tiny orifice. This constriction process superheats the gas, ionizing it into a plasma state, and creates an extremely focused, very narrow, intensely hot jet of plasma exiting the nozzle. We're talking temperatures potentially much higher than TIG, right in the core of that plasma jet.
And this intense focus links to something called the keyhole technique.
Yes. On materials thicker than about 1/18 of an inch, that plasma jet is so concentrated and energetic that it can literally drill a hole, the keyhole, completely through the thickness of the workpiece as the torch moves along the joint. As the torch progresses, the molten metal flows around the back edge of this keyhole and solidifies behind it, creating a very deep, very narrow weld bead. This allows for full penetration, single-pass welds on relatively thick materials, which is very efficient. The main limitation for you as an AMT student or working technician is simply the cost and complexity of the equipment. Plasma arc welding setups are significantly more expensive and require more specialized training than TIG. So you'll typically find PAW used in dedicated manufacturing facilities, not usually in field maintenance or general repair shops. Okay, we've covered the main fusion welding processes. Now we absolutely must be crystal clear on the differences between true welding and the two primary lower temperature joining techniques you'll encounter: brazing and soldering. They're not the same, and the structural implications are huge.
Right. What's the clear, defining line for brazing? How is it fundamentally different from welding?
Brazing is a process that joins metals using a non-ferrous filler material, typically alloys of copper, zinc, silver, etc., which has a melting point above 800 degrees Fahrenheit. That's the arbitrary dividing line from soldering. But here is the absolutely critical distinction. The filler metal's melting point must be below the melting point of the base metals being joined. In brazing, the base metals are heated up, but they're not melted. They only get hot enough for the molten brazing filler alloy to flow into the joint between them, drawn in by capillary action and molecular attraction between the filler and the heated base metal surfaces.
And because the base metal isn't melted and fused, that's precisely why brazing is structurally limited in aircraft applications.
Precisely. Because there's no fusion of the parent metals, a brazed joint relies entirely on the strength of the filler alloy and the surface bond it forms. This joint is always inherently weaker than a properly executed fusion weld in the same base metals. Therefore, brazing is strictly prohibited for repairing critical structural components on aircraft, or for any parts that are subjected to sustained high temperatures, like engine exhaust components where the heat could easily exceed the filler metal's melting point or significantly weaken it. The technique typically uses a neutral or slightly carburizing soft flame, from oxyacetylene usually, requires a chemical flux, often a mix of borax and boric acid, to clean the base metal and promote wetting by the filler. And the crucial technique point is that you must melt the filler rod by touching it to the hot base metal, allowing the heat absorbed by the workpiece to melt the rod, not by sticking the rod directly into the torch flame.
Okay, so brazing is above 800 degrees of Fahrenheit, but below the base metal melting point. Soldering uses even less heat, defined as below 800 degrees Fahrenheit.
That's right. Soldering is also a thermal joining process, using a molten non-ferrous filler alloy, but the key difference is the filler melts below 800 degrees Fahrenheit. We typically talk about soft solder, which are alloys primarily of tin and lead, though lead is being phased out due to health concerns. The classic 50-50 tin-lead solder melts at only around 360 degrees Fahrenheit. Soldering provides very little structural strength. Its main uses in aviation are for creating leak-proof seals on things like copper or brass fluid lines, like instrument lines sometimes, or very commonly for making electrical connections on wiring. And a critical point for electrical work, you absolutely must use rosin core solder. The flux is contained within the solder wire itself, and it's a mild rosin-based flux. You must never use the corrosive acid-type fluxes, like those used for plumbing, on electrical wiring, as the acid residue will cause severe corrosion and connection failure over time.
All right, let's dedicate some specific time now to the challenges of aluminum gas welding using oxyacetylene. You mentioned earlier that aluminum has this nasty habit of just suddenly collapsing without warning. Why exactly does that happen, and how do technicians prevent blowing holes through the metal?
It's really a combination of two main factors working against you. Aluminum's extremely high thermal conductivity, and its almost complete lack of visible color change before melting. First, aluminum conducts heat away from the torch tip incredibly fast, much faster than steel. This means the heat doesn't stay localized. Instead, the entire area surrounding the weld point heats up very rapidly, even if the spot under the torch doesn't start glowing red like steel would. Second, when aluminum finally reaches its melting point, around 1220 degrees Var for pure aluminum, lower for alloys, it transitions from solid to liquid almost instantaneously. There's no gradual softening, no color change from dull red to orange to yellow like you see with steel. It just goes liquid. So the result is you're heating it, seems like nothing's happening, and then suddenly the whole area under the torch, which was already heated close to melting by conduction, just gives way and collapses, leaving you with a big hole.
Wow, that sounds genuinely terrifying for a beginner welder. So, technique and preparation must be absolutely paramount to succeed with aluminum gas welding.
They are everything. For preparation, because of that high thermal conductivity, you typically need to select a torch tip that's one size larger than you would use for steel of the same thickness. You need more heat input to counteract the rapid heat loss. Then, to manage the risk of sudden collapse or blow-through, your torch manipulation technique is critical. You must hold the torch at a much lower angle to the work surface compared to steel, typically around 30 degrees, maybe even less. This low angle helps to spread the heat a bit more and allows you to control the depth of penetration more carefully, trying to melt just the surface layers first to establish the puddle, rather than driving heat straight down through the full thickness immediately. It requires a very steady hand and careful observation.
And flux is mandatory for gas welding aluminum to deal with that tough oxide layer, but it creates its own visual problems, right? The sodium flare.
Yes, aluminum oxide, Al2O3, forms instantly on the surface and has a melting point over 3,700 degrees after, way higher than the aluminum itself. You must use a chemical flux to break down this oxide layer ahead of the puddle. The flux is usually a corrosive powder that you mix into a paste with water and paint onto the joint area and the filler rod. The big visual side effect, however, is a major challenge. When this flux gets heated intensely by the flame, the sodium compounds within it incandesce, producing a brilliant, almost blinding yellow-orange flare. This flare completely obscures your view of the actual molten aluminum puddle underneath it. You absolutely cannot see what you're doing with standard welding goggles. You must use special-purpose filter lenses, typically a specific shade of green glass, like the patented design from TM Technologies mentioned in some sources that are specifically designed to filter out that intense yellow sodium light while still providing the necessary UV and infrared protection. Without the right lens, aluminum gas welding is basically impossible because you can't see the puddle.
Okay, one last point on aluminum gas welding. The tacking procedure. Is it different from how you'd run the main weld bead?
Yes, tacking aluminum requires a slightly different approach than running the continuous seam weld, because you want to get a quick, localized fusion for the tack weld without overheating the surrounding area and causing that dreaded blow-through. You actually use a slightly hotter or more forceful flame adjustment just for the tacks. The guideline is to adjust the flame so the inner cone length is roughly 3 to 4 times the thickness of the metal being tacked. This provides a quick, decisive burst of heat to form the tack instantly, minimizing overall heat input into the part. Then you'd readjust to a softer flame for running the actual seam.
Okay, let's move into the specifics of handling particular alloys that are critical in aircraft structures, starting with the absolute workhorse for traditional airframes. SAE 4130 chromoly steel. What makes it so suitable?
SAE 4130 is a low-alloy steel. The 41 indicates it contains chromium and molybdenum as the primary alloying elements, hence the common name chromoly. The 30 at the end tells you it has a nominal carbon content of 0.30%. This combination gives it a fantastic balance of properties. High tensile strength, good ductility, meaning it can deform without fracturing easily, and importantly, it's highly weldable. This made it, and still makes it, an ideal material for constructing lightweight yet strong fuselages, engine mounts, and landing gear structures using welded tubing. It's relatively easy to work with compared to some other high-strength alloys. It can be welded quite readily by TIG and still very commonly done using oxyacetylene, especially for repairs on older aircraft. Now, when welding 4130 with oxyacetylene, the instruction is very clear. You must maintain an exact neutral flame, no deviation.
Precisely. A neutral flame is critical for 4130. If your flame is oxidizing, too much oxygen, you'll burn the carbon and alloying elements out of the steel, weakening it significantly. If your flame is carburizing, too much acetylene, you'll add excess carbon to the weld puddle, making the weld excessively hard and brittle, prone to cracking. So achieving and maintaining that perfect neutral flame chemistry is paramount. Maybe, just maybe, for certain high nickel chromium alloys like some stainless steels, a slight excess of acetylene and tiny feather might be permissible or even desirable. But for 4130, neutral is the absolute goal. You also need to maintain that soft flame characteristic we talked about and really utilize the outer paler blue envelope of the flame. Let that outer envelope gently preheat the area just ahead of the puddle and shield the molten metal from the surrounding air, minimizing the harmful intrusion of oxygen and nitrogen, which would seriously compromise the strength and ductility of the finished weld.
Okay, now for arguably the most vital safety and procedural point related to welding 4130, especially thicker sections, the requirement for preheating. This seems to be an area where technicians can easily make a mistake if they don't understand the underlying material science, leading to potentially catastrophic structural compromise.
This is absolutely critical and, yes, often misunderstood or ignored. It all comes down to the carbon content and cooling rates. Remember, 4130 has 0.30% carbon. When you heat steel with sufficient carbon content above its critical temperature during welding and then cool it very rapidly, the normal transformation of the internal crystal structure doesn't have time to occur properly. Instead of forming a tough ductile structure like ferrite and pearlite, the carbon atoms get trapped within a distorted, needle-like crystal lattice. This structure is called martensite, and in its untempered state, as formed by rapid cooling, martensite is extremely hard, but also incredibly brittle, almost like glass. It has very poor toughness and is highly susceptible to cracking under stress or impact.
So the rapid cooling caused by the surrounding cold metal sucking heat away from the weld zone creates this brittle structure right next to the weld, the heat-affected zone, HAZ. And the cure for preventing this brittle structure formation is preheating.
Exactly. Preheating is the solution. The rule is generally that any section of 4130 chromoly steel thicker than about 3/16 of an inch, some sources might say 18th inch, always check the specific repair manual, must be preheated before you start welding. You need to bring the area around the joint up to a temperature typically in the range of 300 to 400 degrees Fahrenheit. You can use a torch carefully or temperature indicating crayons, temple sticks to verify. This initial thermal boost does one key thing. It significantly slows down the cooling rate of the weld and the heat-affected zone after you finish welding. By slowing the cooling, you give the steel structure time to transform properly, preventing the formation of that brittle, untempered martensite. Furthermore, there's often a related requirement.
If you're using TIG welding, which tends to have a more localized heat input and potentially faster cooling than oxyacetylene, on 4130 sections thicker than about 0.093 inches, roughly 332, then a post-rolled heat treatment, usually a stress-relieving process around 1100 to 1200 degrees AF is often mandatory as well. This helps to temper any small amount of martensite that might have formed and relieves internal stresses locked in during cooling. Always follow the manufacturer's specific repair procedures regarding pre- and post-heat requirements.
Okay, let's move on to stainless steel. Welding stainless in aircraft structures seems quite limited, and there's a very specific reason mentioned. Cold working. Can you explain that?
Correct. Many structural stainless steel components used in aircraft, things like firewalls or certain high-strength fittings, derive a significant portion of their strength, not just from the alloy composition, but from being cold worked or cold rolled during manufacturing. This process strain hardens the material, increasing its tensile strength considerably. The problem is, if you then take that cold work stainless steel component and apply the intense heat of welding to it, you essentially anneal the material in the heat-affected zone. You undo the beneficial effects of the cold working, causing the material to lose a significant amount of its engineered strength in that area. Therefore, welding on structural, cold work stainless steel parts is generally prohibited. Welding on stainless steel in aircraft is typically restricted to non-structural or lightly stressed components, most commonly things like engine exhaust collectors, stacks, and shrouds, which are often made from annealed, non-cold work stainless steel alloys specifically chosen for heat resistance.
And when you are welding those non-structural stainless parts, what's the technique? Is it different from regular steel?
Yes, the technique is slightly different. For oxyacetylene welding of stainless, you typically want a flame that is very slightly carburizing. Just a tiny feather of excess acetylene, maybe only 1/116th of an inch long, extending beyond the inner cone.
This helps prevent the loss of chromium from the alloy due to oxidation, which is critical for maintaining its corrosion resistance. You also generally need to use a torch dip that's 1 or even 2 sizes smaller than you'd use for carbon steel of the same thickness. Stainless steel has lower thermal conductivity than carbon steel, meaning the heat doesn't dissipate as quickly. Using too large a tip will easily lead to overheating, potentially burning the material or damaging its corrosion-resistant properties. A specialized stainless steel welding flux is also required when gas welding, specifically formulated to dissolve the chromium oxides that form readily on the surface. However, all that being said, TIG welding is by far the preferred and recommended method for welding stainless steel whenever possible. The inert gas shield provided by TIG is much more effective at preventing chromium oxidation than flux is. It eliminates the need for potentially corrosive flux cleanup afterwards, and it generally produces a cleaner, higher quality weld with less risk of damaging the material's properties.
Finally, let's tackle titanium. It's strong, it's lightweight, it's expensive, and it sounds like an absolute nightmare to weld properly due to its extreme need for purity and atmospheric protection.
Titanium presents unique challenges, primarily because when it's molten, it reacts incredibly readily and aggressively with oxygen, nitrogen, and even hydrogen from the atmosphere or from surface contaminants. Even tiny amounts of these elements dissolved into the molten titanium will cause severe embrittlement, rendering the weld completely useless. Therefore, TIG welding is essentially the only practical process and must be done under exceptionally clean conditions with extremely effective inert gas shielding. You typically use DC straight polarity, electrode negative, often with a water-cooled TIG torch because of the high heat reflectivity of titanium. Specialized torch components like a gas lens are often mandatory. These have screens inside the nozzle that help create a very smooth, non-turbulent, column-like flow of argon shielding gas, providing better protection than a standard nozzle. And cleanliness is absolutely paramount. The base metal and filler wire must be scrupulously cleaned immediately before welding, wiped down with specific solvents, sometimes even requiring scraping or brushing with dedicated stainless steel brushes used only for titanium to remove any surface oxides or contamination. Even fingerprints left on the metal can introduce enough contamination to compromise the weld.
And because of this extreme reactivity, the need for shielding goes way beyond just protecting the puddle under the torch. This leads to the concept of triple shielding sometimes being required.
Yes. For critical titanium welds, you often need shielding in 3 distinct zones, and that shielding must be maintained until the metal cools below about 800 degrees Fahrenheit, where it's no longer reactive enough to be contaminated. First, obviously, the primary shield comes directly from the TIG torch nozzle, covering the molten puddle itself. Second, because the solidified weld bead is still extremely hot right behind the torch and still susceptible to contamination, you often need a trailing shield. This is typically a secondary device attached to the torch head that flows additional inert gas over the just completed weld bead as the torch moves forward. Third, you also need to protect the backside or root side of the weld from the atmosphere. This usually requires a backup shielding setup. This could involve flowing inert gas into the inside of a tube being welded, or using special grooved copper or aluminum backing bars that have inert gas flowing through channels underneath the joint. Sometimes temporary enclosures or purge chambers filled with argon are even used for complex parts.
That sounds incredibly complex. And the technician's immediate quality control check for titanium, the very first indicator of success or failure, is purely visual, looking at the color of the finished weld bead.
The color is your immediate diagnostic tool. It tells you instantly how effective your shielding was. A perfect, uncontaminated titanium weld should be bright, shiny silver, maybe with a very light straw color. That's satisfactory. If the weld bead has a darker straw color or a brownish tint, it indicates slight contamination, which might be acceptable depending on the specification, but it's a warning sign. But if you see colors like dark blue, purple, gray, or worse, a dull white powdery oxide on the surface, that means the inert gas purge was fundamentally insufficient. Oxygen and or nitrogen got into the weld while it was hot. That weld is seriously contaminated, embrittled, and completely deficient structurally. It must be completely removed, ground out entirely, and the joint re-prepared and re-welded with improved shielding. There's no fixing a badly contaminated titanium weld. Okay, let's transition now from the specific processes and materials to the practical physics involved in repair work. When you're welding on airframe structures, managing the effects of thermal expansion and contraction is absolutely non-negotiable. It's a constant battle. Uneven heating during welding causes the metal to expand. Then, as it cools unevenly, it contracts. This differential expansion and contraction sets up powerful internal stresses within the material, and these stresses are what manifest physically as warping, buckling, or distortion of the part.
Thin sheet metal seems like it would be the most challenging material in this regard. How do technicians try to mitigate that kind of warpage when welding, say, a repair patch onto a thin aluminum or steel skin?
They primarily use chill bars or heat sinks. These are essentially heavy, thick blocks or bars of highly thermally conductive material. Copper is often ideal because it absorbs heat exceptionally well, but thick aluminum or steel bars can also be used. These chill bars are clamped tightly to the sheet metal immediately adjacent to the weld line on either side of the joint. As you weld, the chill bars act like giant sponges for heat. They suck the heat out of the thin sheet metal very rapidly, preventing the heat from spreading out over a large area. By localizing the heat right at the weld joint and minimizing the temperature rise in the surrounding metal, you significantly reduce the overall expansion and the subsequent contraction forces, thus minimizing buckling and warping. They are essential for controlling distortion on thin materials.
And for welding long seams, like a butt weld down the length of a fuselage panel, maybe 15 inches or more, there's a technique called angular allowance, shown in figure 539. This looks like it's deliberately setting up the parts crooked to compensate for the inevitable contraction.
That's exactly what it is. It's actively managing the physical drawing in effect that happens as a long weld progresses and cools. If you were to set up the two edges of a long butt seam perfectly parallel before starting to weld, as you weld from one end to the other, the cooling and contraction of the completed weld behind the torch would continuously pull the plates together. By the time you got to the far end, the edges would have overlapped significantly. So the angular allowance technique requires you to deliberately space the parts slightly wider apart at the far end of the seam compared to the starting end. The amount of this gap or allowance depends on the material, thickness, and length of the seam. There are formulas or rules of thumb for it. Then, as you weld from the closer end towards the wider gap, the progressive contraction forces pull the plates together, ideally closing that gap perfectly just as you finish the weld. The goal is to end up with a straight, minimally stressed joint by anticipating and counteracting the contraction.
All right, let's apply these principles to the real workhorse of traditional aircraft repair. Welding on 4130 steel tubing structures. Your textbook shows several standard repair methods. Let's take the example of a dent found right at a cluster weld where multiple tubes come together. Figure 546. What's the precise geometric repair procedure specified there?
A dent right at a cluster is serious because it indicates potential damage to the highly stressed junction itself. The standard repair shown involves welding a formed patch plate over the entire dented area. This patch must be carefully shaped to fit snugly over the contours of the tubes at the cluster. It must be made from the same material, 4130, and the same thickness as the heaviest gauge tube that is damaged at that cluster. And here's the crucial geometric rule you must memorize. The fingers, or sections of this patch plate that extend out along each tube leaving the cluster, must have a minimum length. That length must be at least 1.5 times the outside diameter of the specific tube they are covering, measured from the center of the cluster outwards. This specific minimum extension length, 1.5 pax-d, is critical. It ensures that the loads are smoothly transferred from the tube, through the patch, and back into the tube over a sufficient distance, avoiding creating a new high-stress concentration right at the edge of the patch itself.
Okay, that's for dents at a cluster. What about a simpler case, a dent or maybe a small crack located between clusters out in the middle of a straight tube section? Figure 547 shows a welded split sleeve reinforcement.
Right, for damage away from the critical cluster points, a split sleeve repair is often used. First, if there are any cracks, you must stop drill the ends of the crack using a small drill bit, like a number 40 or number 30, to prevent it from propagating further under stress. Then, you try to straighten the dented tube as much as possible. Next, you select or fabricate a split sleeve. This is essentially a tube with the same material, that thickness is the damaged tube, but slightly larger in diameter so it can be split lengthwise into two halves that fit snugly over the original tube. Crucially, the ends of the split sleeve are not cut straight across, perpendicularly. They must be cut diagonally, typically at a 30-degree angle. This diagonal cut provides two significant benefits over a straight cut. First, it creates a much longer weld seam around the circumference of the tube at the end of the sleeve, which dramatically increases the shear strength of the joint compared to a simple butt weld. Second, it avoids creating a sharp, abrupt change in cross-section right at the end of the patch, which could act as a stress riser. The angled cut feathers the transition more smoothly. The two halves of the sleeve are then clamped tightly over the damaged area, welded together along their longitudinal seams, and then fully welded around the diagonal ends where they meet the original tube.
Now, sometimes a tube section is too badly damaged and needs to be completely removed and replaced by splicing in a new section. Figure 548 shows an inner sleeve splicing method. When would you use this, and what are the key steps?
The inner sleeve splice is often used when you need a repair that results in a smooth outer surface on the tube, perhaps for aerodynamic reasons or clearance issues. The process involves cutting out the damaged section of the tube, typically using diagonal cuts again. Then, an inner reinforcing sleeve made of the same material but sized to fit snugly inside the original tube is inserted into the tube ends across the gap. This inner sleeve must be long enough to extend well beyond the cut lines into the original tube sections. The minimum requirement is usually that it must extend at least 1.5 times the tube diameter from the nearest edge of the diagonal, cut into the undisturbed tube on both sides. To secure this inner sleeve, you typically use rosette welds, also called plug welds. You drill several small holes through the wall of the outer original tube into the inner sleeve, and then fill these holes with weld metal, effectively riveting the inner sleeve in place. Finally, the new replacement tube section is inserted between the original tube stubs over the inner sleeve and welded circumferentially at the diagonal joints. There's usually a small gap, like 18-inch, specified between the end of the replacement tube and the original tube stub to ensure full penetration welding into the sleeve.
The alternative splicing method uses an outer split sleeve, similar to the reinforcement patch, but used for joining two tube ends, figures 549, 550. This method seems to require very careful thermal management during the welding sequence to avoid warping the structure.
Yes, when using an outer split sleeve, or sometimes a variation called a fish mouth sleeve for splicing, controlling distortion due to welding heat is absolutely critical, especially on complex structures like engine mounts or fuselages where alignment is paramount. The key principle is weld sequencing and allowing for cooling. You must not try to weld the entire sleeve assembly, both longitudinal seams and both circumferential end welds all at once while everything is hot. If you do, the localized contraction forces as the different welds cool will almost certainly pull the entire structure out of alignment, creating permanent internal stresses and warping. The proper procedure usually involves carefully tacking everything in place first, then perhaps fully welding one longitudinal seam of the split sleeve, letting it cool completely. Then welding the other longitudinal seam, letting it cool. Then welding one circumferential end joint, letting it cool. And finally welding the last end joint. This deliberate sequence, allowing cooling time between major weld steps, helps to minimize the buildup of thermal stresses and maintain the critical alignment of the tubing structure. Patience is key here.
Finally, let's talk about repairs to highly stressed components like engine mounts and landing gear. Alignment is obviously critical here. What are the non-negotiable procedures and limitations when welding these parts?
Alignment is absolutely paramount for engine mounts. They have precisely machined attachment points, and the geometry must be maintained perfectly for proper engine installation and thrust alignment. Therefore, repairs to engine mounts are very often conducted while the mount is still bolted securely to the airframe firewall, or sometimes mounted in a dedicated alignment fixture or jig that holds all the attachment points in their exact required locations during the welding process. This prevents the heat from pulling the critical geometry out of tolerance. A common repair technique involves cutting out the damaged tube section and telescoping a slightly larger diameter replacement tube over the original stub ends, often using rosette welds in addition to circumferential welds for added strength. And here is a critical requirement, often overlooked. If the original engine mount was stress-relieved as part of its manufacturing process, which many high-performance mounts are to increase fatigue life, then any welded repair must be followed by the same stress-relieving heat treatment process. Failure to do this means the repaired mount will not have the required fatigue strength and could fail prematurely. Always check the maintenance manual.
And are there certain components, particularly in landing gear, that are generally considered non-repairable by welding?
Yes, absolutely. Certain components, especially those subjected to extremely high stresses and specialized heat treatments during manufacturing, are typically considered non-weldable for repair purposes. Good examples include the axle stubs on many landing gear struts, which are often made from very high-strength steel alloys and heat-treated to achieve specific hardness and fatigue properties. Welding on these would destroy that critical heat treatment. Similarly, spring steel components, like the main gear legs on some aircraft that act as springs, or certain internal spring components, are generally non-repairable by welding. The heat would ruin their spring characteristics. For these types of components, if they are damaged beyond allowable limits, replacement is almost always the only safe and approved option. Trying to weld them would create an unacceptable safety risk. #outro.
Wow, we have really covered a huge amount of ground today. We've gone through the entire spectrum of common metal joining techniques relevant to aircraft maintenance, everything from managing those incredibly hot 6,300-degree Fahrenheit oxyacetylene flames for traditional steel tube work, right down to the highly precise, non-consumable electrode TIG process needed for reactive metals like titanium, and even touched on the lower temp methods like brazing and soldering.
And hopefully, for you, the AMT student listening, the key takeaway is that the choice of method isn't arbitrary. It's dictated entirely by the specific material you're working on, its thickness, and its structural function within the aircraft. You learned today that while oxyacetylene might still be excellent, even preferred, for certain types of 4130 tubing repairs, TIG welding becomes essentially mandatory for structural stainless steel or for those highly reactive alloys like titanium and magnesium because of the superior shielding and control it offers. And remember that immediate quality assurance check for titanium, the color tells the story. If that weld comes out dark blue or covered in white powder, your shielding failed. That weld is scrap. It must be completely removed and done over correctly.
Absolutely. And maybe the biggest overarching lesson here is that successful, safe welding is often about much more than just the manual skill of laying down a bead. So much of it hinges on those critical non-welding factors: meticulous preparation and cleanliness, strictly following the precise safety limits like that absolute 15 psi maximum working pressure for acetylene, zero exceptions, and adhering to complex but vital procedures like preheating thicker 4130 steel to prevent that brittle martensite formation. And of course, always ensuring those volatile gas cylinders are stored, transported, and handled upright.
Well said. And to leave you with a final provocative thought, something to really anchor this knowledge in the deeper material science principles. We spent a considerable amount of time today discussing the practical methods for minimizing the negative effects of thermal expansion and contraction, using chill bars, angular allowance, weld sequencing. Now, I want you to consider the actual physics calculation for linear thermal expansion. It relies on three factors: the material's specific coefficient of linear expansion, how much it expands per degree of temperature change, the magnitude of the temperature rise it experiences, and the original length of the component. So here's the challenge. Imagine you were faced with repairing a structural joint that involved two very dissimilar metals welded or joined together, say, a piece of aluminum attached to a piece of steel. Knowing that aluminum expands roughly twice as much as steel for the exact same temperature increase, how would you even begin to calculate the immense internal shear stresses that would develop right at that joint line as it heats up during welding and then cools back down? And more importantly, what does that understanding of differential expansion imply for your choice of joining method? Would a high-heat fusion welding process be wise? Or would a lower temperature joining method like brazing, or maybe even a mechanical fastening method, be necessary to accommodate that massive difference in expansion rates? Really thinking through that calculation, understanding those differential expansion forces, that's the true integration of physics and material science into practical maintenance decisions. It's something for you to explore further as you continue to master your craft.